Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on advanced transition metal organometallic chemistry. In today's lecture, we will be talking about transition metal cyclopentadienyl carbonyl complexes. These are popularly known as half sandwich complexes, primarily from the point of view of having a cyclopentadienyl ligand, a metal, and the remaining ligand sites being occupied by carbonyl moieties. So, the name derives from the fact that these cyclopentadienyl complexes, which contains 2 CP rings and the metal, are called sandwich complexes, whereas cyclopentadienyl metal carbonyl complexes, which contains a single cyclopentadienyl ligand, are called half sandwich complexes. Also, these half sandwich complexes or transition metal cyclopentadienyl carbonyl complexes differ from their metallocene counterpart by being heteroleptic in nature, means it contains 2 different kind of ligands, as opposed to the metallocenes, which are binary compounds of cyclopentadienyl ligands, and they are homoleptic complexes and also called sandwich complexes. So, in our last class on these half sandwich complexes of transition metal cyclopentadienyl carbonyl complexes, we have looked into the preparative methods available for synthesizing this compound. The method that we looked at was direct reaction of transition metal carbonyls with cyclopentadiene, resulting in formation of these half sandwich cyclopentadiene transition metal carbonyl complexes. So, we would be discussing more on various synthetic methods available for preparation of these complexes, as well as on their structure and reactivity. So, continuing along the discussion we were having on the synthesis of transition metal cyclopentadienyl carbonyl complexes, we are going to now look at some other examples which are available for preparation of these compounds. The other method involves metal carbonyl plus cyclopentadienyl reagent . For example, reaction of NaVCO6 plus C5H5HgCl, giving rise to C5H5VCO4 plus Hg plus NaCl plus 2CO. Now, this is an unusual reaction as it employs Hg 2 plus as an oxidizing agent. Resulting in the preparation of C5H5VO6 along with the precipitation of elemental mercury. The next method also is along the similar line, reaction of tungsten hexacarbonyl plus sodium Cp, which results in the formation of sodium C5H5 tungsten CO3, and that is a metalate anion. When protonated, gives the corresponding tungsten hydride complex C5H5 tungsten CO3H, and this hydride complex decomposes in light, eliminating hydrogen to give the dimer C5H5 tungsten CO3, and the same dimer can be directly obtained by treating the sodium C5H5 tungsten tricarbonyl with Fe3 plus ion, that itself will get reduced and resulting in the formation of the C5H5 tungsten tricarbonyl dimer. So, this method of getting this dimer from this tungsten metalate is called oxidative dimerization. And is triggered by the presence of iron 3, which acts as an oxidizing agent. So, this is a interesting way of synthesizing cyclopentadienyl iron tricarbonyl kind of complexes by the direct reaction of tungsten hexacarbonyl with cyclopentadienyl reagent. In this case, it is sodium Cp. The next reaction is the reaction of metal carbonyl halide with cyclopentadienyl reagent. So, this is illustrated as follows. Cl, mu Cl, rhodium dicarbonyl dimer plus thallium Cp, cyclopentadienyl thallium in hexane at room temperature gives 2 equivalents of Cp rhodium dicarbonyl plus twice thallium chloride. Subsequent reaction involves cyclopentadienyl metal halide being reduced with a reducing agent in presence of carbon monoxide, that will also give cyclopentadienyl carbonyl complexes. So, the next method involves metal halide plus reducing agent plus carbon monoxide. A nice example of this is shown over here. This is BCP titanium dichloride In this case titanium is in +4 oxidation state. The reducing agent is zinc in THF in presence of carbon monoxide, and NH3 gives the desired BCP titanium di-carbonyl compound plus zinc tetramine dichloride. So, in this case the titanium has been reduced from +4 oxidation state to +2 oxidation state using the reducing agent, which is zinc in this case. Another reaction involves direct reaction of metallocene with carbon monoxide. So, in this case no reducing agent is used. This reaction however requires drastic conditions, as we will see by high pressure and temperature and longer reaction times. For example, Cp2 manganese plus 3 carbonyl in 200 bar of CO 15 hours, 90 to 150 degree centigrade gives this Cp manganese tricarbonyl complex, which is popularly called Cyamtrene. So, this method is a direct method of reacting metallocene with carbon monoxide, and at a very elevated pressure and temperature and longer reaction time to produce this manganese Cp tricarbonyl compound, which popularly is known as Cyamtrene. The last method involves reaction of metallocene with metal carbonyl complexes plus metal carbonyl complexes and the reaction is between nickelocene plus nickel tetracarbonyl compound giving Cp nickel carbonyl dimer plus 2 CO. So, this also is a viable method for synthesizing cyclopentadienyl metal carbonyl complexes. So, what we saw primarily is the reactions that involves the preparation of transition metal cyclopentadienyl carbonyl complexes involved the reaction of either metallocenes directly with carbon monoxide or carbonyl compound, or with a reducing agent in presence of carbonyl compound, or it can also be from metal carbonyls and cyclopentadienyl complexes, or metal carbonyls with cyclopentadienyl reagents, which also lead to the formation of this transition metal cyclopentadienyl carbonyl complexes. Now, we would now look at the structure of this cyclopentadienyl carbonyl complexes. For example, the structure of this kind of compounds are primarily of this type, where you have a CpM CO CO3 MnCO3, or more generally more general formula would be CpMCON. Depending on the metal, the N may vary, and these are called half sandwich complexes. Half sandwich complexes, as opposed to the full sandwich complexes, which are there in metallocene compounds. Also, another notable thing about these transition metal cyclopentadienyl carbonyl complexes, that these carbonyl moieties can act as terminal or bridging. Terminal or bridging, depending upon the metal centers they are bound to. So, I will illustrate this with the following examples. For example, these carbonyl moieties can act as both bridging and terminal when they are bound to 3D metals, whereas they can act as mainly terminals when bound to 4D or 5D metals. So, CO ligand groups can be both bridging and terminal for 3D metals, whereas the CO groups is mainly a terminal for 4D and 5D metals. The reason being very simple: 4D and 5D being bigger than 3D, the bridging binding is not favored. So, I am going to illustrate this in the following example. If M is 3D, then if we CO dimer can have both bridging carbonyl as well as terminal carbonyl. Also, for the nickel complex, it also has the bridging, whereas when the metal is 4D or 5D, then it can act mainly as the terminal carbonyls. For example, for this Cp molybdenum tricarbonyl dimer, this and osmium Cp dicarbonyl dimer, which mainly has this terminal moieties. So, over here this being bigger, they have terminal carbonyls, whereas in 3D it being smaller in size, they can have both bridging and terminal moieties. So, this is very much reflected in this iron Cp dicarbonyl dimer, which has fluxional structure. Fe Cp CO2 whole 2 exhibits fluxional structure, and 4 different species detected by IR and NMR spectroscopy, and that is primarily because of its bridging and non-bridging nature, and also because of its cis and trans isomerism. For example, this compound can exist in following bridging conformation, which is trans, and this is with bridging carbonyls, and also in the cis conformation the way it is shown over here, and non-bridging conformation, the way it is shown over here. So, over here is that this Cp iron dicarbonyl moiety exhibits functionality, and that 4 different kinds of species are observed by NMR and IR, and this is because of various cis and trans isomeric forms in which this molecule can exist, in which this cyclopentadienyl moiety can have a trans disposition to each other, or they can have cis disposition to each other. And also the other possibility is that this carbonyl moiety can be acting as a bridging ligand in 2 of the conformations, cis and trans over here, as well as the carbonyl moiety being totally terminal in nature in the 2 other conformation as shown over here. So, this speaks about the different properties that one can exist, that can arise due to the terminal and the bridging binding of this iron dicarbonyl Cp dimer complexes. So, with this I would like to conclude today's lecture, which had primarily been on various preparative methods available for synthesizing cyclopentadienyl iron carbonyl complexes. These primarily involves 2 types of synthesis, in which metal carbonyls were directly reacted with cyclopentadiene to give the desired complexes, or it can also be the reaction of metal carbonyl with cyclopentadienyl reagents. The other reactions, the other strategies also involved reacting metallocene with carbonyl compounds in presence or absence of the reducing agent to generate these metal carbonyl cyclopentadienyl complexes. Now, as far as the structure and the reactivity of these compounds are concerned, which was also discussed in this lecture, it was found that they exhibit both as a bridging as well as terminal, depending on which kind of metal center they are bound to. For 3D transition metals, the carbonyl tend to exist in both bridging and terminal forms, whereas the carbonyl ligands exist as terminal ligands for 4D and 5D. We have also explained the functional nature of iron CP dicarbonyl dimer, which sort of exists in 4 different forms depending on the bridging cis and trans isomers that can form out of the carbonyl binding. So, with this I would like to conclude today's lecture, and we are going to discuss more on the reactivity of transition metal carbonyl complexes as well as transition metal cyclopentadienyl nitrosyl complexes in the next lecture. So, till then, thank you for being patiently listening to this lecture, and I look forward to being with you in the next lecture. Till then, goodbye.